Why does the cosmos exist? Why is there something rather than nothing? This fundamental question about the universe's birth and meaning has captivated humanity for millennia. Let's begin our journey at the very beginning, the moment we call the Big Bang. More than just a metaphor, it's the most accepted scientific theory describing our universe's origin. Forget the image of an explosion scattering debris. The Big Bang is the expansion of space, time, and all matter from an incredibly dense, hot state. Imagine all the matter and energy we see today, from the smallest atoms to the largest galaxies, compressed into a point smaller than a pinhead. This singularity sounds unbelievable, right? But that's where it all began, about 13.8 billion years ago. In the first fractions of a second, the era of cosmic inflation occurred. Space expanded at an unfathomable rate, far exceeding the speed of light. It wasn't movement through space, but the expansion of space itself. Inflation smoothed out initial inconsistencies and laid the groundwork for the universe's large-scale structure. Without it, the universe would be drastically different, too chaotic or too empty. As the universe expanded, it cooled. The initial energy began converting into matter, elementary particles like quarks, electrons, and neutrinos. These particles were so hot and densely packed that they couldn't combine into more complex structures. The universe was an opaque, hot plasma soup. How can we be so sure about this incredible story? The Big Bang Theory is supported by compelling evidence. One of the most important pieces is the cosmic microwave background radiation, CMB. This faint glow, uniformly filling the sky, is an echo of the hot, early universe. Predicted theoretically and discovered accidentally in 1964, it became one of astronomy's greatest discoveries. The CMB is literally the oldest light we can see, a snapshot of the young universe when it was only about 380,000 years old, and cool enough for light to travel freely. Other evidence includes the expanding universe, discovered by Edwin Hubble. Galaxies are receding from us, and the farther they are, the faster they move. And the observed abundance of light elements like hydrogen and helium, which matches predictions of nuclear fusion in the first minutes after the Big Bang. So, the Big Bang isn't just a theory. It's a cornerstone of modern cosmology. It helps us understand how everything around us arose from almost nothing. It gives us a starting point to ponder why the cosmos exists and how it evolved. Did you know that immediately after the Big Bang, the universe was so hot that stars, planets, even atoms simply didn't exist? After the Big Bang's explosive start, the universe wasn't just hot and dense, it was extreme. Imagine conditions where atoms couldn't even exist. In those first fractions of a second, all the energy from inflation began converting to matter. According to Einstein's famous E equals mc squared, it was the birth of the building blocks of everything. First came the fundamental particles, quarks and leptons. Quarks are the bricks of protons and neutrons. Leptons are electrons and neutrinos. The universe was filled with this primordial soup of particles and antiparticles, constantly created and destroyed, releasing energy. As the universe expanded and cooled, conditions became right for quarks to combine. About a microsecond after the Big Bang, quarks glued together, forming the first protons and neutrons, the nuclei of future atoms. This was a crucial step towards complex matter. The next few minutes were critical. The temperature was still high enough for protons and neutrons to fuse in a process called Big Bang nucleosynthesis. This created the nuclei of the lightest elements: hydrogen, 1 proton, and helium, 2 protons. About 75% of the universe became hydrogen, and about 25% helium. We still see this ratio today, further proof of the Big Bang. However, even with nuclei, the universe remained opaque. Why? Electrons were too energetic to stick to nuclei. They zoomed around freely, constantly colliding with photons, light particles. These collisions prevented light from traveling freely. Photons were constantly scattered. The universe was like a dense fog of very dense plasma. Then came the turning point. About 380,000 years after the Big Bang, the universe cooled to a critical temperature, around 3,000 degrees Celsius. This was cool enough for electrons to lose energy and be captured by nuclei, forming the first neutral hydrogen and helium atoms. This is called recombination. At that moment, the universe became transparent. Once electrons were bound in atoms, photons stopped constantly colliding with them. Light was free to travel unhindered through space. This first light is the CMB we talked about earlier. It still permeates the universe, carrying information about its infancy. The separation of light from matter marked the end of the early universe's dark ages and paved the way for the structures we see today. It was a key stage in the cosmos formation. This will change how you see it. After the first atoms, the invisible but almighty force of gravity began to work, transforming shapeless gas into billions of shining stars and majestic galaxies. After the universe cooled and became transparent, it didn't immediately burst into billions of stars. In fact, a period sometimes called the Cosmic Dark Ages followed. All matter consisted mainly of neutral hydrogen and helium, evenly distributed in vast, empty spaces. But even in this seeming uniformity, subtle fluctuations lurked, tiny regions that were slightly denser than others. These minute differences, seeded during cosmic inflation, became the seeds for everything we see today. This is where gravity comes in, an invisible yet all-powerful force, the main architect of cosmic structures. Gravity has one remarkable property: it attracts. And in these slightly denser regions, gravitational attraction was a little stronger. Over millions and billions of years, these tiny excesses of mass began to attract more and more surrounding gas. It was a slow but relentless process. Imagine giant, rarefied clouds of gas gradually collapsing under their own weight. As these gas clouds became denser, their central regions began to collapse. Under immense pressure and temperature, thermonuclear reactions ignited in the cores of these shrinking gas balls. The first stars were born. These were population 3 stars, incredibly massive, hot, and short-lived, composed almost entirely of hydrogen and helium. They shone in the young universe like lonely beacons, and their short but brilliant lives were immensely important. It was in their cores, under extreme temperatures and pressures, that heavier elements were first synthesized: carbon, oxygen, iron. The very elements that make up us, our planets, and everything around us. When these giant stars died in cataclysmic supernova explosions, they ejected these newly formed elements into the surrounding space, enriching it and preparing the ground for the next generation of stars. Simultaneous with the birth of the first stars, gravity continued its work, gathering even larger clumps of gas and forming proto-galaxies. These giant clouds of matter also compressed, but on a much larger scale than individual stars. Inside these proto-galaxies, millions and billions of new stars formed, which, rotating around a common center of mass, formed the first galaxies. Over time, galaxies grew, collided, and merged, forming even larger and more complex structures. Our own galaxy, the Milky Way, is the result of countless mergers with smaller galaxies over billions of years. This process of star and galaxy formation continues today. In the spiral arms of galaxies, in nebulae rich in gas and dust, new stars are constantly being born, and old ones die, returning their building materials back to the universe. Thus, gravity, acting on the smallest inhomogeneities in the early universe, acted as a cosmic sculptor, transforming a homogeneous gaseous ocean into the amazing and complex cosmic architecture that we observe around us. Billions of stars united into billions of galaxies. Imagine looking at a giant cosmic carousel, a galaxy. Stars on its outskirts are spinning so fast that according to all the laws of physics, they should simply be flung into the void. But they stay put. This observation became one of the biggest mysteries, leading scientists to a stunning conclusion. Most of the universe is invisible and consists of something completely different. We've just talked about how gravity gathers matter, forming stars and galaxies. But what if I told you that most of this gravitational force doesn't come from the matter we can see? This brings us to one of the greatest mysteries in modern cosmology: dark matter and dark energy. Scientists noticed something strange while studying the rotation of galaxies. Stars on the outskirts of galaxies move much faster than they should, based on the amount of visible matter. It was as if galaxies contained much more mass than we can observe, mass that doesn't emit or absorb light, hence dark. This led to the hypothesis of dark matter. We can't see it. It doesn't interact with electromagnetic radiation, light, radio waves, X-rays, but its gravitational influence is undeniable. Think of dark matter as the universe's invisible skeleton. Normal matter, gas and dust, gathered around this invisible framework to form stars and galaxies. Without dark matter's gravitational influence, the universe would be much more sparse, and galaxies might not have formed as we know them. It makes up about 27% of the universe's total mass energy, far more than all the atoms that make up us and all visible objects. But the mysteries don't end there. In the late 1990s, astronomers made another startling discovery. They were studying supernova, exploding stars, to measure the expansion rate of the universe. The expansion was expected to be slowing down due to gravity, but the results showed the opposite. The universe's expansion isn't slowing, it's accelerating. This was completely unexpected and required an explanation. This something that causes the universe to expand at an accelerating rate was named dark energy. If dark matter is the invisible glue holding galaxies together, dark energy is the invisible anti-gravity pushing them apart. Dark energy is thought to make up about 68% of the universe's total mass energy. It's the dominant component determining its global dynamics. What is dark energy? This is perhaps one of the biggest unsolved problems in physics. Maybe it's a property of space itself, a vacuum with some intrinsic energy. Or maybe it's some new, undiscovered fundamental force. We don't know yet. But dark energy determines the fate of the universe. Will it expand forever, becoming colder and emptier? Or does another, unknown scenario await? So, if we want to understand why the cosmos exists and how it works, we can't ignore these two mysterious components. They are invisible, but their influence on the universe's structure, evolution, and future is absolutely fundamental. Imagine that if the force of gravity differed by just 1 part in 10 to the power of 60, or if the mass of a proton was just a fraction of a percent different, the universe would either be empty or instantly collapse. These amazing facts lead us to one of the deepest mysteries. Why are the physical constants of our universe so perfectly tuned for life to arise? We've talked about how the universe was born, how the first particles appeared, and how gravity assembled them into stars and galaxies. But there's one aspect that leaves many scientists in awe: the remarkable fine-tuning of physical laws and constants in our universe. Imagine the universe as a giant cosmic machine. This machine has its levers and buttons that control its operation. These levers are the fundamental physical constants, such as the gravitational constant, the mass of the electron, and the strength of the electromagnetic interaction. It turns out that the values of these constants are perfectly matched to each other to create the conditions for the emergence of complex matter and ultimately life. Take gravity, for example. If it were slightly stronger, the universe would quickly collapse under its own weight before stars and galaxies could form. If it were slightly weaker, matter would never have clumped together densely enough to ignite stars, and the universe would have remained a rarefied gas. Or consider the strength of the electromagnetic interaction. It's responsible for how electrons are held around atomic nuclei, forming atoms and molecules. If this force were slightly different, atoms either couldn't exist at all or would be unstable. In either case, the complex chemistry necessary for life would be impossible. Even the difference in mass between a proton and a neutron is critical. It's very small, but if the neutron were slightly lighter than the proton, all protons would turn into neutrons, and the universe would consist only of neutron stars without hydrogen, which is the fuel for stars and the basis for water. If the difference were larger, hydrogen wouldn't have been able to form. And, of course, the cosmological constant associated with the dark energy we discussed. If it were even slightly larger, the accelerated expansion of the universe would be so fast that galaxies simply couldn't have assembled, and the universe would have remained desolate. All these examples, and there are many more, point to a striking fact. Our universe seems fine-tuned for the existence of stars, planets, complex chemical elements, and life. The probability that all these constants randomly took on exactly the values that allow us to exist is vanishingly small. It's like winning the lottery billions of times in a row. How can we explain this fine-tuning? There are several hypotheses. One is the anthropic principle, which states, we observe the universe the way it is, because only in such a universe could we have emerged and asked these questions. This doesn't explain why the universe is the way it is, but it does explain why we see it that way. Another bolder hypothesis is the multiverse. It suggests that our universe isn't the only one. There may be an infinite number of universes, each with its own set of physical laws and constants. And we just happen to be in one of the rare universes where all the parameters came together so successfully that life could arise. Regardless of the explanation, the very fact of this fine-tuning forces us to look anew at the question, why does the cosmos exist? Perhaps it exists the way it does precisely because otherwise we wouldn't be here to ponder it. We peered into the depths of the universe's birth. But what if the most mind-blowing secrets are still to come? Are you ready to face the idea that our cosmos is just a grain of sand in an endless ocean of realities, and its fate may be far more unpredictable than we can imagine? We've come a long way from the universe's birth to the formation of stars, galaxies, and even the mysterious forces governing its destiny. But our journey wouldn't be complete without looking to the future and pondering the deepest questions that continue to stir humanity's minds. What was before the Big Bang, and what awaits our cosmos in the distant future? Let's start with the future. We know that the universe is expanding at an accelerating rate thanks to dark energy. If this trend continues, we face a scenario known as the Big Freeze, or heat death. In this case, the universe will expand forever. Galaxies will recede from each other so quickly that they will eventually become invisible to us. Stars will burn out, black holes will evaporate, and the universe will turn into an infinite, cold, dark space filled only with rare, scattered elementary particles. This wouldn't be a violent end, but rather a slow fade-out, where all the energy is distributed so evenly that no processes are possible. There are other, less likely scenarios. If dark energy were to become much stronger over time, it could lead to the Big Rip, where the force of expansion becomes so powerful that it tears apart not only galaxies, but also stars, planets, and even atoms. Conversely, if dark energy weakened and gravity took over, the universe could begin to contract, heading towards a big crunch, a return to the singularity from which it once arose. However, current data favor the Big Freeze. And what about what was before the Big Bang? This question takes us beyond the boundaries of standard cosmology. Some theories suggest that the Big Bang may not have been the beginning of everything, but rather part of a larger cyclical process. For example, the result of the collapse of a previous universe, or the collision of branes, multidimensional membranes, in a higher dimension. And here we return to the concept of the multiverse, which we mentioned in the context of fine-tuning. If our cosmos is just one of countless others, then before our Big Bang, there may have been other universes. Or our Big Bang was simply one of many acts of creation in a much larger, incomprehensible reality. This is a bold, as yet unproven idea, which nevertheless offers an elegant solution to many cosmological mysteries, including fine-tuning. Ultimately, the question, why does the cosmos exist, remains one of the deepest and may never be fully resolved. Each new answer raises new questions, but it's this endless thirst for knowledge, this desire to look beyond the horizon of our knowledge, that makes science so inspiring. We are part of this amazing universe, and our very existence is a kind of answer to the question of its purpose. We are its eyes looking into itself, trying to understand why we are here and what it all means. And as long as we continue to ask these questions, the journey of knowledge continues. We've concluded our journey through the most fundamental questions about the cosmos' existence. We hope this story has inspired you to ponder the grandeur and mysteries of the universe. If you're as interested as we are in unraveling these mysteries, diving into distant epochs, and listening to the echoes of the Big Bang. Subscribe to Epoch Echoes and like this video. Together, we'll continue to explore the boundless expanses of knowledge.